All right, we're going to move on to the final lecture for this unit, which is on acids and bases. And what we'll talk about in this particular lecture is the different ways we have of defining what an acid and base is. We'll talk about how to recognize what's an acid and what's a base in a chemical reaction. And then we'll learn a little bit about what we call conjugate acid and base pairs. Right? So that's kind of the three main things we're going to focus on. All right, and we'll start with the Arrhenius definition of an acid and a base. Now, if you guys took sophomore science here at Y, this is the definition you learned, by the way. Okay, so Arrhenius acids, they have a sour taste. They turn litmus paper red. They conduct electricity when in water. And the way we recognize one when written is they have that H plus as a cation. So those acid naming rules, remember I taught you to recognize an acid as H. Whenever we have hydrogen as the cation, we're going to go ahead and call it by its acid name. Okay? So there's a little throwback to semester 1 for you. Right. Now, Arrhenius bases are defined as substances that taste bitter. If you dip litmus paper into Arrhenius base, it turns it blue rather than red. Also conduct electricity. And the way we recognize an Arrhenius base in a formula is with the presence of that hydroxide ion, right? So that OH minus. So if you look at sodium hydroxide, for example, the presence of that hydroxide in those two compounds tells you that those are Arrhenius bases. Okay? And we've done some acid-base reactions actually already that result in a neutralization. Okay, but we'll get to that in a little bit. So what we have to understand, what's actually going on, is first of all, we need to understand dissociation. Okay, so when we talk about dissociation, we're talking about an ionic compound, all right, that when it dissolves into water, separates into its individual ions. So, for example, let's say I take a non-acid sodium chloride. Now, sodium chloride is an ionic compound that will dissolve in water. All right, and so if I put sodium chloride into water, what actually happens is that sodium separates from the chlorine into its individual ions. And the reason that happens is because water is polarity, right? So water has, it's HOH, right? We got a partial negative and a partial positive, right? So those partial charges are able to separate the sodium from the chlorine. The sodium gets attracted to the oxygen side, chlorides get attracted to the hydrogen side. Okay? So when we talk about the dissociation of something, we're talking about an ionic compound that is soluble in water, all right, that when it does dissolve, it separates into the ions that make that compound up. All right? So when we have the dissociation of an acid, right, we're usually talking about, something combined with hydrogen, where hydrogen is the cation. So let's say I have hydrofluoric acid. All right? So when I add hydrogen fluoride, so it's not technically an acid until it's put into water, until it's aqueous, right? So if I see the HFAQ symbol, right, that means I've got hydrofluoric acid, all right, and the AQ means it's been dissolved into water. So what I have to recognize from that is it's not actually a compound of hydrogen fluoride any longer. It is actually hydrogen ions and fluorine ions, okay, that are kind of floating about. And in reality, that H plus attaches to the water to make a hydronium ion. But we'll get to that in a little bit, all right? So it's the formation of that hydrogen ion that's able to be donated to something else eventually that makes the Arrhenius acid an acid. All right, so Arrhenius acids form because we have the presence of that hydrogen cation that is able to be dissociated when put into water. Okay, the dissociation of an Arrhenius base, on the other hand, okay, is when we separate out a hydroxide ion. Right, so let's say I have sodium hydroxide, also soluble in water. All right, so when I dissociate sodium hydroxide, I form a sodium cation, Right, so notice that is not hydrogen, and a hydroxide anion. So it's the presence of that hydroxide anion that makes it what we call an Arrhenius base. All right, so bases, when dissolved in water, generally form hydroxide ions. Acids, when dissolved in water, form hydrogen ions. All right, so that is the basic difference there. Okay, now this does not encompass all possibilities for where there is an acid-base-like interaction. All right, which is why we have what's called the Bronsted-Lowry acids. It's a little bit more comprehensive. Okay, for Arrhenius acids, hydrogen is formed in solution, hydrogen cation. In Arrhenius bases, the hydroxide ion is formed when it's dissolved in water. All right, Bronsted-Lowry defines these a little bit different. All right, and it's a little bit more comprehensive. It encompasses more acid-base-like interactions than what we just saw. All right, now similar to our Arrhenius definitions, Bronsted-Lowry acids donate a hydrogen. All right, now they also define that as donating a proton. All right, and what you have to remember is hydrogen atom is one proton and one electron. If we make a hydrogen ion, we're simply just left with a single proton. All right, that's why we're able to define it that way. Okay, now the bases in the Bronsted-Lowry are just something that accepts the hydrogen ion. Okay, and so that's different. We don't even talk about the formation of that hydroxide ion. It's not that forming hydroxide doesn't make something a base. It's that not every acid-base interaction involves hydroxide. Maybe a way to put that. Okay, so acids are something that are able to give up a hydrogen ion, okay, or a proton, and donate it to something else. Bases are something that will accept that proton. Okay, and so we have lots of different acid-base interactions that show this, and that may or may not involve a hydroxide ion. Okay, so key differences between Bronsted-Lowry definition and the Arrhenius definition is that we do not need to form hydroxides to be a base, and as you'll see in just a little bit, a compound under Bronsted-Lowry theory can sometimes be an acid, but that same compound, depending on what it's mixed with, could also sometimes be a base. All right, so these are kind of our major or key differences between the two different definitions. Okay. So let's look at some examples of how the Bronsted-Lowry definition works. All right. So let's say I have the dissociation of an acid. Okay. What happens is, so let's say I have hydrochloric acid. All right. And I'm going to write this, instead of just saying HCl aqueous, right? I'm going to say I'm adding hydrogen chloride to water. Okay. What's going to result from that? Okay, and I'm going to make little double arrows for our acid-base interactions. By the way, that just means this reaction is reversible. It can go either direction fairly easily, which is pretty common in our acid-base interactions. All right, so if I dissolve hydrogen chloride into water, so I'm going to mix the two, what's going to happen is I'm going to form, so remember I talked about the separation under that H plus and Cl minus, okay? Really what happens with that H plus is it's donated to my water molecule. And what I form is what's called hydronium, H3O plus, and a chloride ion, okay? So in this particular reaction, hydrochloric acid is my acid, and I know that because the H2O becomes H3O. So the hydrogen from hydrogen chloride was donated to the water, okay, in order to make that hydronium ion. All right. So remember, the acid is what does the donating of the proton. The base is what does the accepting. So if I was to label what's my Bronsted-Lowry acid and what's my base, I would say this is my acid and this is my base in that situation. All right, so remember, the key to understanding Bronsted-Lowry acid bases is where's the hydrogen coming from and where's it going to, and that's as simple as that. All right, so let's say I add ammonia to water. So now, in this case, notice that water was our base. It accepted that proton from my hydrogen chloride. Okay, so ammonia, which is NH3, if I put ammonia into water, okay, what's going to happen in this interaction typically is I'm going to get the formation of ammonium and hydroxide ions. All right. So now notice in this case that one of the hydrogens from water was donated to ammonia. All right. And what I formed is that ammonium polyatomic ion. And like a lot of our bases, right, we actually formed a basic solution in that we formed a hydroxide anion. Okay, so in this case, right, water served not as a base like it did in the first reaction, but water served as the acid. It donated that proton. Okay, and this was my base. Okay, so again, it's following where's the hydrogen coming from and where's it going to. Wherever the hydrogen comes from is our acid. Wherever the hydrogen goes to is our base. We're just following the hydrogen. All right, so the hydrogen comes from the acid and it transfers to the base in these interactions. Okay, so another way to look at that is whatever loses a hydrogen, all right, is our acid. All right, and whatever gains a hydrogen is our base. So Bronsted-Lowry acid becomes what's called a conjugate base. So when we look at a reaction, we have whatever started off as our acid. On the other side of that reaction, on the product side, it becomes its conjugate base. So let's take a look at this. So we have HCO3 minus and hydrogen chloride, aqueous, right? In this particular reaction, right? So again, I'm going to draw my double arrows to indicate that this reaction could go either direction, right? Fairly easily. All right. In this particular reaction, what's likely to happen is I'm going to form H2CO3 and a chloride anion. All right. So in this case, the hydrogen was donated to HCO3. So this is my acid. So notice that this lost the hydrogen, and this is my base. Okay. Now, in this relationship, we started with HCl as my acid, so the conjugate base that matches that. So let me do this actually. I am going to change colors. Oops, sorry about that. To red. So this is my base. All right, and let me go back to purple now. Shoot, being stubborn, isn't it? Okay, so here is my original acid, the hydrogen chloride, right? And I know that because this is the atom or the compound that lost the hydrogen. All right, so on the other side, we're left with this chloride ion. So this would be my conjugate base, right? So this acid is connected to this conjugate base. All right. Now, the HCO3 I labeled as my base up here because it is, what accepted the hydrogen in this interaction. All right. Now, as a result, because we're calling this the base, on the other side of this equation, we're going to call that the conjugate acid. All right, so in all of our Bronsted-Lowry interactions, okay, we start with an acid and a base, all right, and the resulting is our conjugate acid, which is paired with the original base, and a conjugate base, which is paired with the original acid. All right, so let's try another one. Let's take our hydrogen carbonate and ammonia, all right, and in this case, sorry, I'm just going to do some erasing real fast here. Again, we're going to have my double arrow, boom, boom. Okay. What we could form in this case is, all right, and just an FYI, for your Bronsted-Lowry conjugate acid base pairs, I'm not going to make you try to guess what's going to accept a proton and what's going to donate a proton, right? I'll just ask you to recognize what's an acid, what's a base, what's the associated conjugate acid, what's the associated conjugate base. Okay, so just a heads up there. That's the way I'm going to structure that for you guys. All right, so in this case, right, we don't know whether, right, ammonia is going to donate a proton or whether hydrogen carbonate is going to donate a proton. Okay, or the bicarbonate ion, excuse me. Okay, so let's say in this interaction what I get is NH4 plus and CO3 2 minus. So let's say that's what I form. All right. So again, I'm not going to make you guess. Let's just say this is what I give you on a test or quiz. All right. What you should be able to do though is recognize which one gave up a hydrogen and is the acid, and which one accepted the hydrogen and is the associated base. All right. So in this case, it's pretty easy to tell that this lost the hydrogen. So this is my acid. All right. And then therefore this would be my conjugate base, right? Whereas this is my original base, and this would be my conjugate acid, all right? So I have a conjugate base acid pair there, and a conjugate acid base pair there, okay? And I think that's the gist of what I want you guys to understand for now about acids and bases. We might get more into the strength of acids and bases at a later date, but for now, leading up to our test coming up here in a few days, that's about the extent of it. Okay, so what does it boil down to for Bronsted-Lowry acid bases? Follow the hydrogen. Whatever gets rid of a hydrogen is the acid. Whatever takes a hydrogen is the base. Okay, and if we're talking about an Arrhenius acid and base, whatever has hydrogens when dissolved in water is your acid. Whatever forms hydroxides when dissolved in water is a base. All right? Keep to it.